In our last video, we were talking about the generalized compressibility chart and how you can find your compressibility factor, which was at capital Z. If it was equal to 1, you could say you have an ideal gas, and then we could use the ideal gas model. Now, let's expand on that and get a few more equations. If our gas obeys the ideal gas law, then we're going to be able to develop this following set of equations. Let's look at specific heat at constant volume. So CV of T, this is just going to be a function of temperature, and it's going to be equal to du dt. And these are specific internal energies here. This is a little u. Now, if you were to go ahead and basically cross multiply like this, you could then integrate, and then that would give you u2 minus u1 equals CV times T2 minus T1. This is going to be one of our equations if we have an ideal gas. This allows you to relate your change in specific internal energy to your change in temperature. Now, we also know that we have specific heat at constant pressure. This is now going to be a function of temperature. It is equal to dH dt. Now, if we do the same thing here, we cross multiply, we'll have Cp times dt equals dH. Derivative on both sides. Let's go ahead and integrate that. And if we evaluate at state 1 and state 2, that's going to give us the specific enthalpy at temperature 2 minus the specific enthalpy at temperature 1, and that equals Cp times T2 minus T1. And I just noticed when I was writing this out, I wrote these in different forms. This is essentially the same thing. I could have just written H2, or I could have written U at T2. Same thing. All right, you're going to find your specific internal energy using your temperature at state 2, for example. So same, different notation, but same concept there. And we are going to have a table that shows the ideal gas properties. This is going to be table A22 in the Moran book. And I'll pull it out and let you see it in just a second. If we look at this table, here's what it looks like. So this is for air. There's another table that has other substances. This one is just for air though. You can see that we've got temperatures here, and it lists your specific enthalpy, your specific internal energy, and then here we've got this other term. This deals with entropy. We'll cover that in chapter 6. All right, so we've got those things, and then we'll cover this when we get to chapter 6 as well. Here we've got another column of temperatures. Essentially there's, the full table here. It's just in this kind of odd format compared to the rest of the tables we've seen. So just note that you have more temperatures and data over here on the right side. But this table provides, like I said, enthalpy and then specific internal energy for ideal gas. If you have air, we'll be using that table to pull information out of there. That's just something to keep in mind so you know where to go when you need it. Now, if we differentiate our H, our specific enthalpy, which is now a function of time, and it's equal to U, which is a function, it's not time, it's temperature, sorry about that. That's going to be equal to specific internal energy, which is a function of temperature, plus R times T. If we take this equation, differentiate it with respect to temperature, what we get is dH dt equals du dt plus R. Essentially, we're just differentiating with respect to temperature on each one of these three terms. And this is what we're left with. Notice the t here goes away because we're taking the derivative with respect to temperature. So when you take the derivative of t, you just get 1. So that leaves r. Now we're left with this. Now if we look up here, we had du dt and we had dh dt. Let's see what we get when we plug in these two equations. dH dt, that is Cp, which remember you have to know your temperature to find the Cp value. And then that's got to be equal to du dt, which is equivalent to Cv, your specific heat at constant volume. So now we've got that, and then we've got R. This gives us a relationship between our two specific heat values. Really the only difference between the two is this gas constant, R. Now this is for an ideal gas. All right. And if you remember before, we talked about the ratio K. Remember that was Cp over Cv. Now we can say that Cp temperature is going to be equal to K times R over K minus 1. This is if we combine it with this equation up here. And Cv of T is going to be R over K minus 1. These will also be equations you might want to highlight. Okay, so now we've developed a few other equations. So ideal gas, if it tells you that, that's going to be another keyword that we need to look for in our problems. Because if we're told that, we know that we can use these relationships. Good stuff to know. Okay, so let's stop there, and in the next video we will do an example. See you then.